Section 6.5 is on operations with radical expressions. We've done some of this before in Algebra 1 and dealt with radical expressions, but this time it's not going to be just square roots. We're going to use it with nth roots. So a couple properties here. The nth root of a times b is equal to the nth root of a times the nth root of b. In other words, if something's multiplied underneath the radical sign, you can pull it apart. Same thing with division. The nth root of a divided by b is equal to the nth root of a divided by the nth root of b. And recall that a fraction cannot have a radical in the denominator. To get rid of that radical in the denominator, we need to rationalize the denominator. Literally, make the denominator a rational number. To do that, we're going to multiply by some quantity that makes the denominator an exact root. And we did this in Algebra 1 with square roots. This time we're going to do it with other roots. Let's take a look at a bunch of examples here. Simplify, number 1, the square root of 72 x to the 8th, y to the 5th. And we did problems like this in Algebra 1. So we're going to start with 72. Square root of 72 is not an exact number, so I'm going to factor tree that. A lot of different ways you can do that. 8 and 9, 2, 4, 2, 2, 3, 3. And because, excuse me, we're taking the square root, we're looking for pairs of numbers. So here's a pair. Here's a pair, and this guy doesn't have a buddy. So I can have a 2 out front and a 3 out front, and then I'm going to have a square root of 2 still underneath the square root sign. X to the 8th, that's actually an even number, and I'm taking the square root of that, so that's going to give me x to the 4th. And let's check and see if we need to do absolute value bars. I'm doing the even root of an even power, but I'm getting an even answer, so I don't need bars. Y to the 5th, so that's equal to y squared times y squared times y. So each of those y squareds can come out front, but then it's going to leave me with a square root of y. Okay, so let's check that one. So I did an even root of an odd power, so no need for bars. So let's combine stuff. So the stuff that is out front is going to be 2 times 3, which is 6, and x to the 4th. This is going to turn into a y squared, and then the two things that are underneath are the square root of 2 and y. So I can multiply stuff underneath and then multiply the stuff out front. And there's my final answer. Okay, number 2. So now we have the 4th root of 162, a to the 6th, b to the 13th, c. Okay, so 162, I'm going to start breaking that down. And since nothing pops into my mind, I'm just going to start with 2 because I know it can be divided by 2. So 2 times 81. 81 is 9 and 9, and 9 is 3 and 3. And because this is a 4th root, I'm looking for groups of 4. And sure enough, right here is a group of 4 3s. So I'm going to have a 3 out front, and then this 2 here is going to have to stay underneath the radical sign, so I'll have a square root of 2 there. Oh, not square root, sorry, 4th root. Okay, a to the 6th, so that's 6 a's. I'm not going to write them all out. So 4 of those will group together and can come out as 1a, but then there'll be 2 a's that are still in the radical sign. Okay, and let's see, so I am doing an even, I do have an even root of an even power, and I did get an odd answer, so I do need to put bars around that. Okay, now b to the 13th, I could think of that as like b to the 12th times b to the 1. So b to the 12th is going to give me, the 4th root of that is going to give me a b to the 3rd, and then I'll have a 4th root of b. And then c to the 1 is just going to leave me with a 4th root of c. And as I did with square roots, I can take all of the stuff that's not underneath the radical and put that together. So 3 times the absolute value of a. Just a hint, when you're making your absolute value bars, make them bigger than like a 1, so they stand out as bars. And then I have a b cubed, and then in the radical, I'll have a 2 and an a squared and a b and a c. And there's my final answer. Kind of funny looking, but actually, believe it or not, that is simplified. Okay. Next example. This one's a little more complicated. We have the cube root of 6x squared divided by the cube root of 5y. Now the problem with this is I have a radical in the denominator. I have the cube root of 5y on the bottom. So what I really need to do is I need to get rid of that radical sign. What I would really like to have on the bottom is just a plain old 5y. Okay, so I want this to be just a 5y. So what do I have to multiply the cube root of 5y times to get just a plain old 5y? Is what I have to ask myself. So remember, this means that I have something times itself 3 times gives me 5y. So since I'm going to need another cube root of 5 squared y squared. Because what that's going to give me then is the cube root. Now when I multiply these, I'll have 5 to the third, y to the third, and that's going to give me my 5y. So what do I need to multiply this by to get a 5y? So I'm going to multiply the top and bottom by this expression right here. The cube root of, and I'm going to actually simplify that a little bit, 25y squared times the cube root of 25y squared. Okay. Now the point of this is to get just a plain old number on the bottom, plain old expression, numbers and letters, no radicals. Okay, so when I multiply across the bottom, as I showed down here, that's just going to give me a plain old 5y, which is what I want. And then on the top, I can multiply these two because they're both cube roots. It's a little messy, but just go ahead and multiply the cube root of 6 times 25 is 150. And I cannot break that down anymore because 6 is 2 and 3, and 25 is 5 and 5. X squared, y squared. And that's my final answer. So rationalizing a denominator with a square root, you probably remember from Algebra 1, with a cube root or a fourth root or some other power, a higher index, it's going to be a little more complicated. So you'll remember also from Algebra 1 that in order to add or subtract any radical expressions, the radicands must be the same. Okay, so I need to simplify these and then combine what kind of look like any coefficients out front. So simplifying 5 squared of 12. This is a 4 and a 3, and the square root of 4 is 2, and 3 can't be simplified, so that's the square root of 3. Okay, this is going to turn 27 is a 9 and a 3. So the 2 out front, square root of 9 is 3, and that's going to, and I don't have anything for the 3, that needs to stay square root of 3. 128 is 64 and 2. You could do a whole factor tree here, but I think if you can recognize some perfect squares that are factors of the radicand, it would be really helpful. So 128 is 64 times 2. Square root of 64 is 8, and then we have a square root of 2. Okay, let's simplify by multiplying the stuff out front. 10 square root of 3 plus 6 square root of 3 minus 8 square root of 2. Okay, because I have the same radicands here, I can combine those, and I'll just add the 10 and the 6 to give me 16 square root of 3 minus 8 square root of 2. So here's a multiplication problem, and actually it kind of looks like we're multiplying a couple binomials here, but technically they aren't. But we do use the same method that we do if we are multiplying binomials, and that is foiling. So I'm going to use FOIL for this. Okay, so when I multiply my first, I'll have 2 square root of 3 times 3 gives me 6 square root of 3. My outer, 2 square root of 3 times a negative square root of 3 gives me a negative 2 times 3, which is 6, because square root of 3 times square root of 3 just gives me a 3. Okay, inner, 3 square root of 5 times 3 gives me a positive 9 square root of 5. And then doing my last 3 square root of 5 times negative square root of 3 gives me a negative 3, and I can multiply the square roots, square root of 15. Now let's look at what we have. None of my radicands can be, they're not the same. In fact, 15, if I simplified that, it would just be a 3 and a 5, so that can't simplify any further. In this case, there's nothing else to combine, and that's my final answer. You'll also recall from Algebra 1 that if there's a radical in the denominator and a plus or a minus, so not just a radical there, but could be an integer added or subtracted to a radical, or in this case, two radicals, we need to multiply by the conjugate, which is the same two terms that are in the denominator, but with the opposite sign between them. So in this case, the conjugate is going to be the square root of 5 plus 3. I'm sorry, square root of 5 plus the square root of 3. Okay, notice the same numbers, square root of 5 and 3, but instead of the minus, I'm going to have the plus. On the top, I'll distribute. So 2 times square root of 2 times square root of 5 is square root of 10. Square root of 2 times square root of 3 is the square root of 6. And now what happens on the bottom is when I do my inner and my outer, they're going to cancel each other out. That's going to give me a negative square root of 15, and this is going to give me a positive square root of 15. I want that to happen, so I really only have to do my first terms, which is going to be square root of 5 times square root of 5, which is 5. And my last terms, negative square root of 3 times a positive square root of 3 gives me a negative 3. And then I can simplify that to square root of 10 plus the square root of 6 over 2. And I remember you cannot add square root of 10 and square root of 6. And in fact, neither of those can be simplified any further. So that would be my final answer. So in this section, we took a look at some operations with rational expressions, kind of building on what we learned in Algebra 1 and adding higher indexes and basically using the same rules that we did back then.